Okay. Again, it's the mathematics of graph. Basically, we're going to focus with graph theory. Graph theory class is simply, it is a branch of mathematics, another area of specialization in the field of mathematics, which actually deals with the network of points. Okay. It deals with the network of points connected by lines. Okay, so the graph theory here, graph theory is actually a branch of mathematics which deals with the network of points connected by lines. Please do understand that the line we're talking about here is a non-Euclidean. It's a non-Euclidean line because when you say Euclidean lines, it's actually a line or line as defined in the book of Euclid, the elements, that whenever you have 2 points connected together, then you have a line. But the line we're talking about here is not actually Euclidean, but rather it is a non-Euclidean line. Any point that are connected, still defined as any point connected with two, I mean connected together, but it doesn't necessarily mean that it's a straight line because Euclid defined a line as 2 points connected together, then you form a straight line. So it's that's but in this case, the lines that connect the points here is not necessarily straight. Okay, so the concept of graph theory is actually well versed. I mean, it's widely spread and applied also in different branches or applied in different areas. It's applicable in the field of computer science, social sciences, chemistry, operations research, and other fields. Accordingly, in the field of computer science, graphs are used to represent networks of communications, data organizations, computational devices, the flow of computations, and others. One good example is the link structure of a certain website, which could be represented by a directed graph. The vertices are the web pages that the websites are directed edge from page X to page Y exists if and only if page X contains a link to page Y. So basically, this is just trying to convince us that graph theory or graph in general is actually found or applicable in several fields such as computer science, mentioned also in chemistry. In chemistry, remember there are bindings of um, the pictures in chemistry when there are um, the binding of elements, and then uh, yeah, the lines there that connects the dots, those who are actually concepts expressed and explained by the so-called graph theory. Now let's go to defining the term graph. Who has an idea what graph is? Now, graph theory is a branch of mathematics that focuses on connection or connected dots or points connected by lines or network of points connected by lines. Now, let's talk about graph specifically, which is actually the heart of graph theory. What is graph? Actually, accordingly, graph G, okay, as defined, graph G here is our arbitrary element that we name the graph. Because basically we can name the graph any capital letter for that matter. But to make a general statement, we call it graph G. Graph G consists of a non-empty. Okay, it's a non-empty finite set. Take note, we have here the word finite, we have set. Non-empty, in other words, there exists a single element in it found. So when you say finite, it's limited. And then set, of course, it's a collection of a well-defined object. So in this case, we're talking of a collection of a well-defined objects, such as the points and the lines that makes a graph. Okay? So that is a graph. Graph G consists of a non-empty finite set of the following. Um, Set of V of G, okay, which is called the elements, called vertices, okay? The vertices, or also known as nodes or nodes. So when you say graph, it composes of vertices or vertex, plural form is vertices, are also known as nodes or node, and again a and finite set of E of G. You notice this is actually a set. The set E here is defined to be the an of an ordered pair pairs of called edges or edge family or edge family. Okay, so that what makes a graph. It comprises of a set of vertices and a set of edges. The vertices here are our points, network of points that were connected with lines, and the lines here are called the edge or edges, or also known as the edge family. So the vertex set for graph is denoted by this notation, which is the V of G. The V of G, whenever we encounter this notation, V of G, it implies that the set containing the vertices of graph G. So the name of the graph is G, and whenever we encounter this notation, it simply refers to the collection of uh, all the vertices in G, okay, or on G. So that is what the vertex set is, and then the edge set is, which is denoted by E of G, like this. Still the same graph, this one, the same graph that we're talking about. But whenever we encounter this notation or whenever we express it in this notation, we're referring to the collection of all the edges or the edge family for graph G. Okay? So again, emphasizing that one, that G is simply consisting of uh, set of vertices and set of edges. Okay? So if we're gonna write it this notation for example, since it is a set, I'm sure we discussed already what or how we would write set. So when we have it V of G is simply the collection of V1, V2, V3 ellipses. Okay? I sorry, that should end with V sub n. Okay. So V of G is a set containing V sub 1, V sub 2, V sub 3, until V sub n. You notice there is V sub n here towards n because we defined earlier that it's finite. That's why I changed it to V sub n here, because if I'm going to leave it as ellipses, this is by the way called ellipses. I'm not sure with the spelling though. Just go over with the spelling. It's called ellipses. If I'm just going to end with an ellipsis, it implies that it goes to infinity. So it doesn't end, or the last term is not even identified. But when I use V sub n here to be my last term, I'm pretty sure that there is an end of that element, and that element must be the the last member of this set, the last vertex that we can identify. So anyway, this is how we're gonna write the elements for this set, which refers to the vertex or the vertices of graph G. Whenever we have also E of G, that refers to the E1, E2, E3. Okay, that's the edge one till is until E sub n. Again, E sub n because this is a finite. Because when I talk about graph, there is an end to it. There is at least its finite collection of the edges and edge family and the vertices. So we have here the vertices, the vertex set and the edge set. Now let's take, for example, this particular graph. Example I'll have here. Okay, example, this is my graph. Let's say this is graph G. By the way, we name the vertices here as using small letter. So we have, let's say this is A, B. Take note, there is no node or vertex here. Okay, as I did not made a shading here. So I have B, C, D, E, F, G. So these are the vertices of the graph. And then I have here, this is, um, okay, let's name now the graph here. When they say vertex G, so the vertices of G, so that means to say we have A, B, C, D, E, F, and then we have G. Though that is, these are the elements of our vertex set, the vertices of graph G. Now, how do we name the, uh, what do you call this one, the edge? For the edge or the edge family, we name our edge family is produced whenever we have two vertices connected or whenever there is a line connecting the two vertices. And we call that, we name that edge using the two vertices. For example, if we name this edge A to E, so we call that as one edge, which is A, E. We can actually, even if we interchange E, A, that still refers to the same edge, which is this edge here, connecting vertex A and vertex E. Okay, so that's one of the vertices, one of the edges, followed by, okay, I have again A, F, and then A, F, then we have F or B, F, what else? B, F, then I have B, G, and then G, E, and then I have E, D, and then I have E, C, D, C. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 edges with 1, 2, 3, 4, 5, 6, 7, 7 vertices. Am I correct? 1, 2, 3, 4, 5, 6, 7. Okay, we have 7 vertices and 7 edges for graph G in this function or in this particular graph. Any questions so far in identifying the vertices and the edges of a given graph? That's why I told you that the graph and then the line here that connects the vertices does not necessarily mean straight. Okay, as uh, as per graph theory is concerned. Uh, is there any question or clarification about this particular concept and how we identify the vertices and the edges of a given graph? Okay, I think there is no question. Now let's talk about the so-called order. Okay, what is order? Order class refers to the number of vertices. Okay, order of the graph is the number of vertices, and each size is determined by counting the number of edges in a graph. Okay, so order is the number of vertices, while size is the number of edges in a graph. So we have order, then we have size, number of edges. So for example, graph G. Graph G here is of order. We are actually going to write it as like this. For example, this one. Graph G here is of order 7. Okay, order 7 with size 7. Because we've got 7 vertices and we also got 7 edges. That's why we called it. Graph G is of order 7, size 7. 1, 2, 3, 4, 5, 6, 7. Okay, so again, when you say order of the graph, that refers to the number of vertices found in the set or in the graph. And then size is the size of the graph is the number of edges there is. Okay, now two vertices of a graph are considered neighbors. Okay, we have this the term here neighbors or adjacent. Sorry. So adjacent or neighbor. Okay, two vertices are neighbors if there is an edge connecting them. If an edge connects them. Okay, so an adjacent or neighboring vertices are edges or rather vertices which were connected with or which was connected with at least one edge. Okay, we have the edge DC. So DC here are adjacent vertices because there is an edge connecting. The edge that connects them or that made a DC neighbors is actually edge DC, rather DC or DC or CD, because what makes D and C neighbors is the edge DC. By the way, this edge now is called the incident edge. Incident edge for neighboring vertices AC, a DC rather. So what makes DC neighbors is edge DC, which is called incident edge for neighboring vertices D and C. Okay? So the edge that made two vertices neighbor is called incident edge. Okay? And what made two vertices neighbors is the incident edge. The edge that connects the two vertices. Next, at the same time, we have also adjacent or neighboring edges if they are connected with or if they share one vertex or there is one vertex that is common to them. For example, uh, in this case here, this one, uh, D and C are adjacent or neighbors because of DC. That's why DC is your incident edge for neighboring vertices of D and C. In this case, at the same time, we have CD and DE are adjacent as well, or neighbors. Adjacent or neighbors. Because of the common vertex D. So because of D, CD and DE are neighbors. And we call D here as our incident vertex. Incident vertex. Okay, they follow? So what I'm trying to say here is that we have incident vertex and we have incident edge. An incident edge is the edge that connects two neighboring vertices, and then an incident vertex is a vertex that is common between neighboring edges. Okay, there is a common vertex that there is a common vertex between these edges, and that is vertex F, which is called the incident vertex. Okay, I think that's already clear, and I hope everybody were able to follow the concept of incident vertex and incident edge as well as we connect it with the neighboring vertices and the neighboring edges. A, B are they are not edges, they're vertices. It should be edges. So we have A, for example, AF and
B,
BG.
G. Okay.
Basically, they are non-adjacent because first is they don't share any common vertex. Well, obviously
Yes.
they are non-adjacent because by definition, edges are adjacent if they share common vertex. Surely, looking at the vertex, the edges here, there is no common vertex. It follows that the two edges are non-adjacent. Now have the so-called multiple edges or parallel edges. What is multiple edges or parallel edges? Okay, by definition, parallel edges is simply edges. A pair of vertices consists of more than one edge. Okay, so we have one or more edges. No, we have at least two edges connecting them. For instance, example, this one, edge D E, edge D E, or rather, vertex, vertices D and E. Okay, so this is an example. Sorry, we don't have multiple edges here or parallel edges. Actually, we don't have multiple edges. My bad. Sorry, sorry. I thought D and E are connected. But if we're going to add here one more, for instance, like this, so D and E are considered as vertices with parallel edges. Okay, D and E are vertices with parallel edges. Parallel edges meaning to say that you have two or more edges that connects D and E. That makes vertices D and E as vertices with parallel edges. So when you say parallel edges are simply edges that were actually um, bound and were that is two or more edges that is actually connects the same vertices to the same vertices. It's called parallel edges or multiple edges. But in this example, since I added a vertex to an edge to D and E through this path, through this direction, then it's called D and E are considered vertices with parallel edges. As D and E are actually parallel edges because we have DE through this route and we have also DE through this route. Okay, that is an example, or that is a parallel edges. And at the same time, there is what we call a loop. What is a loop? Loop is a vertex, or a vertex is considered, we will have a loop when we have a vertex or we have an end whose beginning vertex and end vertex are the same. Okay, that's a loop. For example, if I'm gonna put here something like this, for instance, like that, this is a loop because our this vertex or this edge here is G to G. So meaning to say it moves around from G and it goes back to vertex G. So it's considered a loop. And then basically a graph without a loop, it's a loop-free graph. Okay? Question. So we discussed already parallel edges. We discussed also what a loop is. Now let's talk about the degree of a vertex. degree of a vertex, which is known as dig, and then let's say A. A here is your example. This is A. A here is the vertex, and then dig here is this is the notation. Dig A, referring to the degree of vertex A. Dig A, or the degree of a vertex, refers to the number of edges incident, okay, incident to that vertex. So how many edges that is incident to A, that's the degree of the vertex. Example A here. A here, there were two incident edges to A, so that means to say this is considered as 2. So dig A is 2. For there are two incident edges to A. In other words, there are two vertices connected to A. No, there are two edges connected to A. That's the degree of A. We only have edge BF and edge BG. That makes now vertex B with degree 2. So actually it's 2, and then the degree of A is 2. The degree of C, D, E, F, and then we have G. 1, 2, 3, 4, 5, 6, 7. So we have 7. Can I just remove this one? Actually, I just placed this earlier just to explain to you the parallel edges, but this was not actually present here during the first example. So there were 7 edges, and then we have also 7 vertices. And then I also remove the loop first because this was not here. What the degree of vertex C is 1, right? Because there is only one edge that connects there that is incident to C. For D, we have, sorry, this is only 1. For D, we have 2, which is the edge DB and DE. And then for E, we have 3. We have edge EG, DE, and AE. Okay, so we have 3. For F, we have 2. For G, we also have 2. That's the degree now. By the way, this is called the degree sequence. The sequence, uh, by the way, the degree sequence is the arranging, the increasing order of the degrees of the vertices. So in this case, we should have it 1, 2, 2, 2, 1, 2, 2, 2, 2, 2, 3. That's the degree sequence of the vertices. So the degree sequence now, the degree sequence of graph G is, we have 1, 2, how many 2? 1, 2, 3, 4, 5. 2, 2, 2, 2, 3. This is the degree sequence of graph G. And this is the degree of each vertices. And then as we arrange them in increasing order, then we have 1, 2, 2, 2, 2, 2, 5 twos, and then 1, 3. So you notice we have 7 vertices, and then the degree of the vertices is actually 1, 2, 2, 2, 2, 2, and 3. Okay, this is the degree sequence. This is the degree of each vertices. Question. Next is we have the isolated vertex. What is an isolated vertex? Isolated. From the term itself, isolated, in other words, alone. When you say alone vertex, it's a vertex without any edge incident to it. In other words, if I'm going to put here vertex, let's say M, M here is an isolated vertex because in graph G, we have actually a vertex that we're not, or that is not connected to any other vertices in the graph. So we call that vertex as an isolated vertex. And then lastly, an end vertex or pendant is a vertex, okay, that is pendant. Pendant. Pendant is, example is C. Pendant is a vertex with a degree of 1. When you have a vertex with degree 1, it's called pendant or end vertex. Meaning to say, that's the end of it. There is no more. If you are going to make a route through that path, you'll just stop there. You can no longer move forward because that's the end of the route. Something like that. So in this example, we have C here as our pendant or the end vertex. And then M here, as we added, is an example of our isolated vertex. Okay? So we talk about the order of the graph. By the way, the order of the graph can be written as, like, example, this is graph G, and then graph G is um, 7, 7. 7, 7 here, implying that this is order 7, order, and then this one is the size. So when you will encounter G, when you have an encounter rotation like G, and then there's a ordered pair 7, 7, or the ordered pair here, the pairing is, the first is the order of the graph, and then the next one is the size. So we have here graph G of order 7, size 7. Okay? Just emphasize that one because I think I forgot to mention it earlier. But if this is our new graph now, this one, G1 here is actually a graph with order 8, size 7. Because actually we have 7 edges, but since we added here one more isolated vertex, then we changed the order now to 8. So we have here graph G1 as of order 8, size 7. Okay, that's it. Question.
Sir, katong na parallel sir, parallel sir ba katong pareha katong sa
Parallel
DE gani.
edges.
Yes, sir, parallel edges. Apilon to sa
Wow.
account. Sir.
Parallel edges are counted twice,
Okay, sir.
but loop is counted once for the edges. Later, we will talk about the one when we will learn the different theories in corollaries in graph theory. Now let's have this theorem. Okay, theorem is a mathematical is a statement that is proven true in the field of mathematics. The theorem says that in a graph G, the sum of the degrees of all the vertices is twice the number of edges. I sorry. I already erased. Let's just make another graph. Let's have this graph. A, B, C, and then we have D. So this is F. Okay. If we are going to record now the degree, we have degree of A, and then B, C, D, E. We don't have E. We have F. So the degree of A is 2. The degree of B is 2. C is 2. D is 3. And then F is 1. Now, and then the sequence here, the degree sequence is 1, 2, 2, 2, 3. According to the theorem says that in graph G, accordingly in graph G, the sum of the degrees of all vertices is twice the number of edges. Okay, so according to this theorem, In graph G, or whatever, in a graph, the sum, okay, the sum of the degrees of all the vertices is twice the number of edges. Now let's identify, this is example, this is graph G. Let's change this graph. Let's say this is graph R. In graph R, what is the order of graph R? The order of graph R is order and size.
5 order.
Okay, we have five. What's the size? Is it 5, 5? Right? It's 5. We have one, two, three, 4, 5. Okay, we have 5. So we have here in in graph R the order and then size. The order we have our graph R here of order 5 size 5. According to the theorem, in this graph or in a graph, the sum of the degrees of all the vertices is twice the number of the edge. So in this case, the sum of this, let's get the summation. 2 plus 2 plus 2, that's 6. It's 10. According to the theorem, when you double the number or the size of the graph, that is equivalent to the summation of your edges. So 5, the size here is 5. That's the number of edges. So 5 times 2, it gives you 10. No wonder that the summation of our degrees is 10, according to the theorem. So it's guaranteed that whenever you have a graph, in any graph for that matter, get the summation of the degrees of all the vertices. That is double of the size. So in this graph, graph R, the size is 5. Double the 5, that gives you 10, which is exactly the summation of the degrees of the vertices. Okay. Another, we have a corollary. Corollary class is an extension. It's a proven statement as an extension of any theorem or any proven statement. So it's like whenever this, since this is proven true already, so there is like an extension to this one. We call it the corollary. According to the corollary, okay, it's an extended proven statement to be true based from a given statement. The sum of the degrees of the vertices of a graph is an even number. Okay, the sum of the degrees of the vertices of a graph is an even number. Okay, definitely it is true because when you get the sum of this one, according to this corollary, since this is true, the sum of the degrees of all the vertices in any graph for that matter will always gonna be even. Why? Remember that according to the theorem, the summation of the degrees of all the vertices is twice the size. The idea here of twice, so any number that is twice or at least multiplied to 2 will always gonna be even. That's what the corollary is telling us. So it's guaranteed that whenever or the sum of the degrees of the vertices will always be even because it is in fact uh, equivalent to double your size of the graph. Another corollary. In a graph G, the number of odd degree is even. Corollary, this is corollary 1, corollary 2. Corollary 2 is still an extension of this theorem. Since the sum of the degrees of all the vertices is twice the number of edges, then we have these two corollaries or two true statements as an effect of this statement. So this statement says that in graph G, in graph G, the number of odd degree is even. Take note of the word even. So since this is true, this is the effect of this true statement, that the summation or the summation of the degree of the vertices is always even, and then at the same time, the number of odd, okay, the number of odd degree in the given graph is always even. So it follows. You look at this one. These are the odd degrees in our degrees of the vertices. And how many odd degrees do we have? We only have two, which is an even number. It's always guaranteed that whenever we have a graph, the odd degrees or the odd degree is always even number. So it's either 2, 4, 6, 8, 10. Those are the only odd degrees that you will encounter in any graph because of this theorem that was already proven true for any graph. Any question about the corollary? I mean the corollary, the theorem, the corollary 1 and corollary 2 and the theorem. Please, you ask question. I think there is no question. I'll just skip the type of graphs because the bar part type graph. Oh, I think I really have to go through this definition. Okay, let's go now discuss the type of graphs. There are different types of graph. First, if we have the simple graph is a graph without edges, no, without vertices, wait. Simple graph is no loop, no multiple edges. That's a simple graph. Okay, no loop and no multiple edges. So the first example that I have earlier was a simple graph because there is no loop, there is no multiple edges. Example of a simple graph is like this. A, B, C. So this is an example of a simple graph because this graph does not contain any loop. Okay, a loop is a graph wherein there is an edge that is whose beginning and end vertices are just the same, and then multiple edges is two or more two vertices with two or more edges that connects them. In this case, is an example of a simple graph. Another type of graph is actually a multi-graph. Multi-graph is basically a graph with multiple edges. That's why it's called multiple graph, a multi-graph. So example of this is a graph example like this. A, B, C. So that is like this. Okay, this is an example of a multi-graph because we have several edges that connects vertex A to B, as much as we have also several edges that connects vertex A and C. That's why it's an example of a multi-graph. We have the next graph, which is the pseudo-graph. Pseudo-graph. What is a pseudo-graph? A pseudograph is a graph with at least one loop. So for example of this is if this is A, this is B, connect that one. Then I have C here, for instance, C. And then if I have here a loop, and then there's a loop here, then this is an example of a pseudograph. Pseudograph meaning to say a graph consisting of at least one loop. Next is a trivial graph. Trivial graph. A trivial graph is simply a graph with one vertex and no edge. So example, this is A. This is an example of a trivial graph because there is a vertex and so happen that there is no edge. Okay? So that's an example of a trivial graph. Next is a regular graph. What is a regular graph? Regular graph is a graph with all the vertices. Graph with has the same degree. All vertices have all vertices same degree. Okay, do you follow? So this graph is not a this is not a regular graph, but if I'll have it like this one as an example, A, B, C, D. This is a regular graph because remember the degree of B, A, B, C, D, all the degrees, all the vertices have the same degree, which is of degree 2. And then if you add it, that's 8, which is the sum of the degree. Following the theorem, it's even. And then um, the order or the size of this graph is 4. Double the 4, that's 8. That's following the theorem as well. So this is an example of a regular graph. Any graph with the same degree is called a regular graph. Or any graph with vertices of the same degree is called a regular graph. An empty graph, what is an empty graph? Empty graph is simply a graph with no vertices, no edges. So no, nothing at all. That's an empty. Okay? It's called an empty graph. Take note, a trivial graph is not an empty graph because there is a vertex. So no edges, and then no vertices. That's an empty graph. While a null graph, in this instance, a null graph is a different story. A null graph is a graph whose edge set is empty. So in other words, whenever you have a graph with E of G equals empty, no element at all, then that's an example of a null graph. This is a null graph. A trivial graph is a null graph. Another example, if you have A, B, then you have C. 3 vertices, A, B, and C. Since there is nothing or there is no edge that connects the vertices A, B, and C, then this is an example of a null graph. Okay? Question. There are still other graphs, but I'll just have to skip those other graphs. I'll just move right away to the types of, we have the walk, trail, we have paths, path, and then we have circuits, and then cycle. What are these terms? Okay, let's start with a walk. A walk is simply, um, it's a walk from one vertex to another, passing an edge. Okay. Example of a walk is here. A, B, C. So a walk is from A, B going to B, C. A, B, then B, C. This is a walk from this vertex to this vertex passing A, B, B, C. This is an example of a walk. Okay? So it's any route that you're going to take, so long as there is a route. Meaning to say there is somewhere you can walk. Because if there is no S, then they cannot perform any walk at all. No wonder that in a trivial graph, you cannot perform any walk at all. Because there is no path, there is no edge to take. Okay, that's a walk. So a walk is from vertex to vertex. Sorry, my definition of walk is wrong. Vertex walk is from A to B to C. That's an example of a walk. And then this is C. Next is we have the trail. What is trail? By the way, before I'll continue, this is your initial vertex, initial vertex, and this is your terminal. So it's like the concept of terminal is your endpoint. So it's like the door terminate. So this is your initial, that's the beginning vertex, and then your terminal is the end vertex in any walk. If I will start my walk from C, B, and going to A, so this is my terminal, this is my initial. Okay? So the arrow will all actually indicate where you're heading or how the walk is being performed. But definitely, can I perform a walk from C to A? No, this is impossible because I don't have any route connecting C to A. If I'll perform a walk, I should have passed B going to A. Okay, that's why this is, or not a walk, not a walk. Because no edge connecting A to C or C to A. Next is we have we still have the length of the walk. What is length? Length of the walk is the number of edges in a walk. So in this case, the walk from A to B, from A to C is length 2. Because there are two edges that I have to pass by. So this is 1, 2. So it's called, the walk from A to C is of length 2. For there are two edges that I passed by. Okay? Next is a close walk. What is closed walk? A closed walk is a walk wherein your beginning vertex is also your end vertex. If there is an example, there is an edge here. So if I will perform a walk A to B, B to C, C to A, so if I will end here with A, then this is a closed walk. A, B, C, and A. It's a close walk because my end vertex and terminal vertex are, I don't know, my initial vertex and terminal vertex are the same. So it's a closed walk. An open walk is this one. Example, um, this walk here. A, B, C. This is an open walk because I did not end where I started. So it's an open walk. Open walk. Example, A, B to C. It's an open walk because I did not end where I started. A closed walk is a walk wherein I end from where I started. So that's a closed walk. Okay, let's now talk about the so-called trail. What is trail? Trail class is simply a walk with no repeated edges. No repeated edges. So, example, A to B to C is an example of a trail because I did not make any repetition of edges. Another example is A, B, C to A is another example of a trail because first and foremost, I did not, my walk is like this, A to B, B to C, C to A. It's a trail because I did not pass by the same route. So that is a trail. Next is we have path. What is path? Path is a walk with no repeated vertices except possibly the initial and the terminal vertex. So path is no repeated vertex. So in this case, A to B to C, no repeated vertex is an example of a path. Okay? So no repetition of, so this one is also an example of path as this is example of A B, C to A. This is also a path. In the sense that the only exception in a path is when you have a closed walk, um, all the paths are all paths can be closed walk. So the only thing that is not, but not all closed walk is necessarily path or trail at the same time. No, but path and a trail are all walk type of walk. Okay, so that's a path. What is a circuit? Circuit is simply a vertex to itself. It's actually a trail that is a closed trail from a vertex. So this is an example. This is an example of a circuit. Circuit. Meaning to say, no repetition of edges and it's closed. So it's a closed walk or it's a closed trail. Circuit is a closed trail. Closed trail. That is a circuit, a closed trail. Now, when you say cycle, cycle is a closed path. Okay? Wait, I think it's a closed path in a closed trail. Mhm. Wait. Cycle is a circuit that do not contain any repetition of initial. Okay. Cycle is a closed trail with no repetition of vertices. So it's like a combination. Cycle is a path and a trail at the same time. Okay. Cycle is a path and trail at the same time. No repetition of vertex, no repetition of edges. That is a cycle. So whenever you have a walk that is a path and a trail at the same time, then that is a cycle. Okay? When you have a closed walk with no repetition of edges, then that is a trail. If you have a closed walk that is not, you know, when you have a closed walk with no repetition of edges, then that is circuit. So just remember that the cycle is a path and a trail at the same time, while a path is simply a type of walk with no repetition of vertices except the initial and the terminal, while trail is a walk with no repetition of edges, while cycle is a walk which is a path and a trail at the same time. Okay? I hope you were not confused on that concepts. I before I'll dismiss, I would like to emphasize when it comes to the order of the graph and then the edges. For the counting of edges, loop is counted once, but trail is counted. Multiple edges is counted as they are, but loop is counted once in terms of the number of edges. That's why when it comes to the order of the graph, loop is counted. Example, this is the graph. If I will have here like this, so this graph is actually um, order 3, size 4 because of the loop. Okay? Let's try to double check this one with the degree. So the degree here, dig A is 2, B is 2, C is 3, 2. Alright, wait. Wait. I think there's something wrong. No. This is 3. In terms of the order, uh, wait. Let me put it all together. Yeah, that's correct. That's correct. The size is 1, 6. Yeah, yeah. It's like this. You look at this one. When it comes to the order of the graph, actually the loop is the tricky part here. When it comes to the graph, the size is the number. The size is the number of edges. I know the order is the number of vertices, so it's three. Why I have four? It's like this: 1, 2, 3, 4. So 1, 2, 3, 4. So in this case, I have four edges. The loop is counted. Wait, four. In terms of edge, the size, loop is counted once. But in terms of degree, it's counted twice. It's like this. The degree 1, 2. The degree of A is 2. The degree of B is also 2. The degree of C is actually 4. That is 1, 2, 3, 4. Because we're talking about the incident edges to the vertex. So that's 4. The total is 8. Double of this one is still 8. Okay? Now, please just make sure to fully comprehend what is the case of loop, because the loop is somehow the tricky part in counting the number of edges. Just always anchor your idea, your understanding to the theorem that the sum of the edges should always be even, and the number of odd degrees should be even, and then double of the summation of your degree uh, is I don't know. The twice of your size is the summation of your degree. Okay. So again, I'll repeat for this one. In this case, the size of this graph is 4 because, or the size of this graph is 4. It's because we have 1, 2, 3, 4. Okay, that's the size of the graph. But the degree of vertex C, there are 4 because we have 1, 2, 3, and 4. Okay. And still that follows the definition or the theorem that we have earlier. I hope I made the clarification clear to all of you.